Anyway, what I would like to do today is finish the examples from yesterday. I have a demonstration that we're going to take a look at in order to answer one of these questions. And then you're going to be using the remainder of the class to complete all of the assigned work dealing with this topic of projectile motion. Keep in mind, every single example that we're looking at here with projectile motion involves objects being launched horizontally from a particular height above the ground or above the water or whatever the case is. What we are going to be doing on Monday is looking at what happens if you launch an object at an angle. So for example, when I hit a golf ball with a pitching wedge, if the ball simply goes horizontally, then I have to practice, right? The pitching wedge is supposed to launch the ball up, so the ball goes up and down. In either case, what we have learned, and it's absolutely crucial, is whatever's going on horizontally does not affect whatever's going on vertically. I mean, they're connected by the same time, but if there is an acceleration downward of 9.81 meters per second squared, that's not going to affect the motion horizontally. And in the end, what we said, and this will be true on Monday, what we said is that because of that, you analyze things horizontally and vertically independent of each other. What you're dealing with here is uniform motion, which means you have quantities that you can talk about like speed, distance, and time, or if you want to get fancy, velocity, displacement. Well, I don't think I should put a vector symbol above the time. Time is time. Whereas over here, what you're talking about is uniform acceleration. Ran out of room. That's okay. You know what I mean. And that means that on this column, what you're referring to is things like VI and VF and A and D and T. And what I've said to you is the directions are not really that important here with these problems, but starting Monday, they're going to be. Because if we go back and we think about what we did with those kinematics equations, when we didn't use vectors, we didn't include direction, it was because the objects were simply moving down or in one direction. As soon as the objects went up and down, we had to use negatives if things were negative. And when I launch a ball from the fairway with a pitching wedge and it goes up at an angle, it's not going to accelerate up at 9.81 meters per second squared. It's going to accelerate down. The acceleration is going to be negative. If you put a positive into the equation will think. Equations don't think, but I think you get my drift. The equation is going to believe that you mean the object is going to continue to speed up towards the sky, and it won't. So when we'd solve this problem, your setup would be to say, I'm going to throw a ball a horizontal distance from one place to first base, and the horizontal distance is 10.6 meters. So we can put this 10.6 meters here. During the flight, the ball drops 1.8 meters. When a ball player throws a ball to first base, they do not throw the ball up, generally speaking. They throw it pretty much horizontal to begin with. If you're throwing a ball from center field to home plate, yeah, you're going to launch it because you'll get a bigger distance, you'll get a bigger range. But when you're trying to get somebody out at first base, you have to get the ball there as quick as possible. You're not going to throw the ball to first base and throw it up at an angle of 80 degrees, right? So it goes way up and then down. You're going to throw it lightning fast horizontally. But if you watch that ball, if you play baseball, you'll know this. When I throw a ball somewhere, it's going to fall during its flight. Not much, necessarily. Depends on how fast you throw it. 1.8 meters in this case, negative 1.8 meters. I want to pause for a second because I just said something that I think might cause some people some confusion. I started off by saying these two things are independent of each other, right? But then I just said how much it falls depends on how fast you throw it. And that is true because if I want to throw the ball 10.6 meters and I throw it at a very, very low speed, it's going to take a longer time to get there, and that means it will fall more. I mean, they're connected to each other because the time is the same. We just analyze them separately. What else do we know? We know the acceleration due to gravity is negative 9.81 meters per second squared. And the initial velocity in the vertical dimension or vertical direction is 0 because it's launched horizontally. On Monday, it will no longer be 0 because we're going to be launching objects up at an angle. So when you solve this problem, you take this kind of problem-solving approach that I'm asked to find. What am I asked to find? How fast it was thrown. I'm asked to find this. But when you take a look at this information, which is connected by speed equals distance over time, or velocity equals displacement over time, it doesn't matter in this case, you're missing the time. Well, how do you find the time? Well, you do a kinematics calculation over here on the right-hand side, and the equation that you can use is displacement equals 1/2 acceleration times time squared. You know, and again, you don't need the vectors in this question, but starting Monday, we're going to need the vectors. So I'm just deciding today to put them in. I'm going to go with an assumption here that, well, I assume everybody can put these numbers in and solve this for t. Briefly, if I put the d in, negative 1.8 meters, I think. Yep. Equals 1/2 times negative 9.81 times t squared. Again, I'm leaving the units out because I want you to be able to get the answer first and foremost. You multiply that displacement by 2 and divide by 9.81 and take the square root. My calculator is going to be over there probably. Yep. Personally, if I'm doing this on my calculator, everybody, oh, it is there. It showed up. Thank you. Thank you for letting me know that because I would have been confused when I got over there. Personally, when I'm doing this, I would just leave out the negatives. And it's not because I don't need them. It's because mathematically I can see that they're going to cancel anyway. Okay? It's not that I don't need them because of the physics. It's because I don't need them because of the math. Who cares? However, if that bothers you, I'll take the displacement, multiply by 2. I need to divide by negative 9.81. Again, I personally, I wouldn't put those negatives in. I need to take the square root. So I'm getting for a time here about 0.6 seconds. Anybody else up for that? Okay. So 0.6 seconds. 0.606. Okay, I can put that here. The whole point of doing this, again, it's what I always say. Yes, the ball accelerates towards the surface of the earth. Yes, the ball moves towards horizontally first base. But it's not two baseballs doing two different things. It is one baseball accelerating towards the surface of the earth and moving at a certain speed to first base at the same time. So these two times are equal. You just put the 0.606 here, and we're going to divide that 10.6 meters by that time. About 17.5 meters per second. Are we okay with that? Okay. How many of you, I asked you to give that one a crack if you wanted to. How many of you were able to get that? Okay. So the remainder of you, is it safe to say it's not that you were unable to get it, you just didn't give it a crack? Okay, that's fair enough. How many of you feel as though if you had that ambition last night and you cracked your physics books open, you would have gotten the question right? Okay. We're going to go back to number 5 now. Actually, you know what? We're going to go back to no. We're going to go back before the examples. There was a question at the bottom of page 38. two objects are released at the same time from the same height, say 2 meters. I normally do this as a demo and I use about 2 meters, but we're going to do it from about, I don't know, 6 meters or 7 meters. Okay? One of these objects is simply dropped and the other is simply fired horizontally at a speed of 4 meters per second. So what's going on here is we've got a particular height. It doesn't matter what the height is. We have some countertop or it could be a building, I don't care. And what we're going to do is we're going to end up releasing two objects simultaneously. And maybe in order for you to see this a little bit better, I'll draw it this way. We are going to take one of these objects and it's going to be released from that height. And it's just going to fall straight down. And we're going to take the other object and we're going to fire it horizontally at a speed of 4 meters per second. So of course, this object is simply going to fall straight down, clink, hit the floor. This object is going to follow some kind of arc. And if we knew the height, we could do the mathematics and figure out, how far away it's going to land, whether it's going to be this tiny arc or whether it's this big arc. We could do that. But I'm not worried about that. And the question is, these are two different objects. This isn't one object doing two things. These are two different objects. Which will hit the ground first? Which will hit the floor first? No?
In an ideal situation, they hit the ground at the same time.
Say that again?
They would hit this on the ground at the same time if it was like a perfect situation, I think.
Well, let's assume it is perfect. Why would it not be perfect?
Air resistance.
Air resistance. If these objects are pretty tiny, we haven't talked too much about air resistance, but you understand that if I'm walking through the hall, I can feel the air on me, and that's friction. It's actually slowing me down. You can imagine instead of walking through water up to here, and I'm walking through. It's hard, right? It's hard to walk through water because there's a resistance. Air is a little thinner, so the resistance isn't that big. That force of friction with the air on me is usually not significant. And 4 meters per second is not a big enough speed to create enough friction to make it not ideal. By the way, as you go faster and faster, the friction becomes more apparent, right? Like when you're running, you can feel it. It's not really slowing you down that much. But I hope you would agree that 100 kilometers per hour is a pretty significant speed in terms of force of friction with air. Don't do this, but if you unrolled your window and you're driving down the road at 100 miles per hour and you stuck your arm out suddenly, you will discover that there is a significant force of friction there, right? It's gonna push your arm. So let's go back to what Noah said. They will hit the ground at the same time. Why is that?
Because it's the same gravitational pull.
So they're both being pulled down, but at 9.81 meters per second squared. But this one has an initial velocity of 0, right? The one on the right has an initial velocity of 4 meters per second. That's a true statement, by the way.
You said that X factors and Y factors don't really mix in that way.
Right. You know what we're back to here? We're back to the boat in the river and me saying, regardless of how fast the river flows, the time it's going to take to reach the other side is going to be determined by the speed of the engine. And if it were a rocket propelled, where we had that acceleration of the boat, the only thing that's going to determine the time it takes to reach the other side is that acceleration and the fact that it has an initial velocity in that direction of 0. So if what I've told you is true, where am I? There we go. If what I've told you is true, it shouldn't matter that that's 4 meters per second or 40 meters per second. The difference would be that this ball is going to land directly below where it was dropped, and this one will land some certain distance away. Now, if it were 40 meters per second, in theory it should take the same time, but it's going to land even further away. So we're going to go over into the atrium, and I have this set up on the second floor by the elevators there, and we're going to try it. Now you need to keep something in mind. Let me show you the apparatus here first of all. This is the apparatus. So I have these two spheres. They're metal balls. This one is sitting in, there's a little hole drilled in the metal platform, so it's sitting in there. That's going to cause a little bit of a problem because this has got a lever on a spring on it, and I've pulled it down and locked it, and when I flip this up, this pin is going to move to the top of the screen. And what's going to happen is this sphere on the left is going to be kicked out by the pin, and the sphere on the right is going to just fall because the pin is sitting in the sphere. The pin's just going to retract and the sphere will fall. But because this sphere on the left is sitting in a little hole, it's not sitting on a perfectly flat surface. So when that pin hits it, it moves up just a little bit, just not much. So I'm saying all of this because I want you to understand that, forgetting about air resistance, this is not a perfectly ideal situation, but it's as close as we can get. And the nice thing about using these metal spheres is you hear them hit the floor. Right? You're going to hear a clack when I pull the pin, and this rod retracts and kicks one object out and then drops the other one. But you'll be able to hear them hit the floor. So we're going to go over there. It'll take me just a minute to go upstairs and set this up. But let's head down there and let's check it out. I'm sure I'll be able to find a video showing the hunter-monkey experiment. As I said, we don't have it here. It's just a little too... It'd be nice to have it, but we spend our money on a lot of other things that are just as useful or more useful than one demonstration like that. So I'll find a little video and we can talk about that a little bit, but I hope that made sense. If we take a look at number 5, and I believe we skipped over number 5. Yeah. So let's take a quick look at number 5. A ball rolls off a tabletop that is 175 centimeters above the floor. How long does it take the ball to reach the floor? If it is moving 1 meter per second when it leaves the tabletop. That's 1 meter per second horizontally. Well, when we take a look at the y motion, vi is 0. Acceleration is negative 9.81 meters per second squared. The displacement of the ball is going to be 1.75 meters, and it will be in a negative direction. Again, I guess I actually maybe made a bit of a teaching error yesterday by saying we don't need to worry about the negatives, because then this morning I thought, yeah, but we will on Monday, so why don't we use them all the time, okay? And what else do we know? In our list we have VF, but who cares? We're not asked about it. We don't know it. Is there anything else we know vertically about the motion of this object? I've got that. It's negative 1.75 meters. Well, be careful here. Negative 1.75 meters refers to the displacement that the ball or the object will undergo, but there's something else we know. The initial speed vertically is 0. And then if we were to write out the horizontal, we would have horizontal, and we would have speed, distance, and time, or velocity, displacement, and time. And we would put 1 meter per second here, right? So how are we going to find the time it takes to reach the floor? We're going to look at the vertical kinematic aspect of things. And that's why I've kind of washed this out when I wrote x. That's not relevant. This is why the two balls will strike the ground at the same time. Whether it's dropped, whether it's moving horizontally at 1 meter per second or any other speed, This time will be found by using d equals 1/2 at squared. And I would hazard a guess here that many of you are maybe getting bored is an exaggeration, but you're getting a little bored of using this equation. It's just becoming old hand, it's like your hand. You're very familiar with it, right? So I would like everybody to calculate that time. You're going to take 2 times the negative 1.75, then you're going to divide by 9.81, and get probably close to 0.6. I'm leaving the negatives out because mathematically I know they're going to cancel. Don't forget to take the square root. About 0.60 seconds. Okay. See, I think having all of the discussions we had with the other examples yesterday, this totally makes sense. Yep. All of this is starting to make more sense because we've already talked about this numerous times. If I take a look at B, what if the ball was traveling or the object was traveling at 10 meters per second when it left the tabletop? Well, I'm assuming that, and you guys had a legitimate concern in the atrium, is the ball going to hit the wall? I'm assuming this has got enough space to clear without hitting something on its way to the right as it leaves the tabletop, and it's going to go arcing nicely into the floor. The answer to the question is 0.6 seconds. Right? Because, and some of you will take this approach, it's because what determines the time is the vertical acceleration and the height. Some of you will take this approach, and fair enough, I'm okay with it. I didn't have to use x, so apparently it doesn't matter. That maybe shows a little less understanding of why it doesn't matter, but in either case, that's it. And I think we did not do 7 either. Am I right? Okay. So, and is 7 the last question? Well, 7 and there's an A and B or 8. Yeah.
And that's all.
Okay. So a bullet is fired horizontally with a speed of 450 meters per second. Now we are taking a lot of liberties here with our assumptions. There is a fair amount of friction initially with a bullet moving through the air, but it's not significant enough to change things. Okay. By the way, 450 meters per second is faster than the speed of sound. Which means, and this is a reason why hunters will use high-speed bullets, and they're also used, in other areas in the world, but hunters will use high-speed bullets because the animal will get hit with the bullet before the animal hears the shot. This is moving faster than sound. By the way, when you hear a gunshot, that's the bullet breaking the sound barrier. When you hear a lightning bolt, that thunder, that's something breaking the sound barrier. Have you heard of a sonic boom? Okay. A sonic boom is when something travels faster than the speed of sound. And what happens is the sound in front of the object is moving away from the object, but if the object gets faster and faster and breaks that, all of those sound waves get piled together, and as it passes that, you get that huge release of energy. Anyway, if I fire a bullet with this speed at an animal, it will hit the animal before the sound gets there. There will be an impact, and then a short time later, there will be a bang. The target is 300 meters away. How much higher than the target should you aim? This is not a monkey that's going to fall from a tree, okay? The target is stationary. You need to aim higher than the target because the bullet is going to drop. I'm not sure. I mean, I don't want to get too much into all of this because it's a little off topic. But there's scopes on rifles. And I don't know if you've seen movies that snipers will adjust the scope. They will estimate the distance and then they adjust the scope so that when they're looking through it, the rifle is actually aimed up. And there's numbers on the dials on the scope that you can adjust to move it up based on your estimate of how far the distance is. That way, when you're looking through the scope at the object, you are actually aiming a little bit higher. Your scope is pointed down a bit, so you have to raise the rifle to see the object. Because if you don't do that, if you don't take that into account, It's going to fall. The bullet's going to hit lower than you want it to. Anyway, again, maybe way off topic, but I think some of you might have found that interesting. We've got horizontal, we have vertical. The horizontal distance or displacement is 300 meters. By the way, just look at the speed. This bullet is going to be falling for close to a second. Not exactly, less than a second. But it has to go 300 meters and it's traveling 450 meters per second. It's about 2/3 of a second, I think, if my estimate is right. So it's going to fall. The speed of the bullet horizontally is 450 meters per second. The initial velocity vertically is 0. The acceleration due to gravity is downward, and it's 9.81 meters per second squared. The vertical displacement is what we are after, but there is not enough information in the vertical column for us to answer the question. So what do? Close our books and go home? No, you say, how can I find something else in the vertical column? Well, I can find the time, because the time is the time. It doesn't, whether you talk about the bullet moving towards the target horizontally or the bullet falling as it does that, those times are the same. So time here is equal to displacement over speed. Can you do that for me? Yeah, it's going to be 2/3 of a second. 300 divided by 450. It will be 0.6 repeating, I think. All right. So that means the bullet is in the air for 0.6 repeating seconds. We can put that here. And now we can do a d equals 1/2 at squared calculation. Keep in mind, if you don't put the negative for acceleration, you will get a positive answer, but it's a displacement downward. It falls that distance. I think here's where we might want to really stick to the vector idea. Oh, 0.5 times negative 9.81 multiplied by 0.6 repeating. That's good enough. Squared. Looks okay. Oh, I was off by a decimal. About negative 2.2. That's surprising, isn't it? I mean, I find it surprising the first time I see something like this. You have to aim 2 meters higher than 2 meters. I'm 2 meters tall. Well, no, but this is 2 meters tall, right? I don't know. You'd have to get out a meter stick and check it out. That's a pretty big distance. The time is very small, but we know, I mean, clearly if I said take out your phone and try to time the time from here to that clack, it happens quickly, right? Apparently in about 2/3 of a second. So, how much higher does the hunter or the marksman have to aim above the target to hit the target? They have to aim about 2.2 meters above the target because the bullet's going to fall 2.2 meters. What 2 physics principles were used? We did this already with a previous question, I think. Like we've talked about this before. So the main idea here is that when you're doing a calculation with vertical motion in these problems, it is uniform acceleration. That's just a summary. I want to go back and show this to you. When you're doing a calculation with the vertical motion for projectiles, it's this is your y. And when you're doing the calculation for the horizontal, it's uniform motion, that's your x. So in answering this question for number 7, what did we do first? We did a calculation first over here to find the time under x, which is physics principle 0. Then we did physics principle 1, which is uniform acceleration. Would you agree? Okay. So we would answer here on the exam, 0, 1. All right. I still haven't wrapped my head around this new schedule, but I'm thinking you have a lot of time here, 40 minutes left-ish. Briefly, this is a review. I don't know if that page number is right. We'll get to that in a second. Is it right? It is, okay. This is the basic idea that with projectile motion, you treat the horizontal and the vertical aspects separate from each other. That the horizontal is uniform motion, which means zero acceleration, which means you use things like speed, distance, and time, or velocity, displacement, and time. Whereas, and this is the only formula you can use. That's it. Whereas over here, with uniform acceleration, you use descriptions like initial velocity, final velocity, displacement, acceleration, and time, because there's accelerated motion. And this part where I say VI is equal to 0 is true today. Because of the problems we're working on today, that's true. But on Monday, when we start talking about objects that are launched at an angle, the initial velocity will not be 0 because it will, if I launch an object up at this angle, as soon as it leaves my hand, it's moving to your left, it has a horizontal velocity, and it's moving up. So that will change. And the equations that you use here, I'm not going to write them down, I guess. D equals 1/2 AT squared is, I think, the only one you end up using so far. Right? There are other equations you could use. Like if I said, what velocity does it hit the ground at, you could use a different equation. Anyway, that's it, 1 to 7. I'm going to take a quick peek at your textbook, and I might give you a few more additional problems to practice. But if you finish a little early today, you finish a little early today. I don't care. I want you to have a good, solid background for what's coming on Monday. And I'm also going to see if I can find a hunter and the monkey. Not a real monkey. Okay? So get started on that, please, and I will be back to help you in a few minutes. Carter. Of course, yeah. Of course, yeah.